Well, it's a great pleasure to welcome Chrysoula Markou. I'm sorry, I'm mispronouncing your surname again.
Perfect. No worries.
She is joining us today from Athens, where she's from originally, and she's a postdoc with Dieter Lust in the Max Planck Institute in Munich. And thank you very much for joining and agreeing to give this seminar. I'll hand over to you.
Right. Thank you, Denjo, very much for this very kind invitation and for the opportunity to present our work at your institute. So I will speak about a project that I initiated and led and worked on together with Dieter Lust, Stefan Stieberger, who are permanent researchers in Munich, as you very well know, and also Puriya Maslumi, the PhD student of Stefan Stieberger. And the title of the project is Extracting Bigravity from String Amplitudes. Basically, I will take you on a trip from field theory to string theory and back. In particular, we will consider spin-2 fields. So in ghost-free bimetric theory that describes massless and massive spin-2 fields field theoretically. Then from fields, we're going to go to string theory and calculate string amplitudes, and from those extract effective actions and compare those to the bimetric theory prediction so as to see what kind of interactions are governed by string theory as far as spin-2 fields are concerned. So let's start with an introduction, and that is how we think of gravity. We think of gravity in the sense of the metric theory of Einstein, of what Einstein formulated as general relativity. And in particular, in that theory, there is a metric field, which can alternatively be seen as a particle, as the quantum of gravity. So let's take a simple example. If one starts with minimal assumptions, those as being Lorentz invariant and locality, so just write all Lorentz invariant and local terms that one can for a massless rank 2 tensor, around Minkowski spacetime in the simplest case, and further impose that there are no ghost or in general unhealthy degrees of freedom propagating, then one gets uniquely diffeomorphous invariants. And in fact, this can be promoted to arbitrary backgrounds to yield GR. So GR, it can be viewed either as the metric theory of gravity or as the unique kinematical theory of the metric tensor that is a massless Helicity-2 spin-2 field. Okay, and that is due to many authors. Now, this is as far as field theory is concerned, but in fact, we very well know that there is an embedding of this theory in string theory. And in particular, this quantum of gravity is identified with particular states that appear in closed string spectra. So let's see the simplest example that Scheck and Schwarz put forward. And that was to consider the bosonic string, the closed bosonic string, where states are constructed out of bosonic oscillators, transverse bosonic oscillators acting on the vacuum. And in particular, the first massless, the massless level that appears, the only set of states that appears in this spectrum that is massless, contains a symmetric combination that can be identified with a metric. That is what Scheck and Schwarz originally proposed. Now, further, they, and also later with Green and Brink, and further with Gross and Sloan in the context of heterotic string theory, they calculated string amplitudes describing, if you want, the scattering of this kind of state, the symmetric combination of the massless state that appears in such closed string spectra. And they calculated those amplitudes involving 3 and 4 external legs, and from those extracted the respective effective Lagrangians. And in fact, it turns out that those are nothing other than the lowest order terms that appear in the expansion of the Einstein-Hilbert term. That is actually the action for general relativity. So they confirmed that the quantum that is part of Einstein's theory and fundamental part of Einstein's theory is equivalently well at low energies described by closed string states in the context of string theory. And this is ubiquitous, in fact. So in all closed string spectra, one can find a symmetric massless combination that corresponds to rank 2 tensor that can be identified with a metric. All right. Nevertheless, Einstein's theory leaves several questions unanswered. For example, those that are related with dark matter, dark energy, the nature and value of the cosmological constant. And this is why several modifications of Einstein's theory have been put forward. One of these is ghost-free bimetric theory. So what is its most generic action? It is this one here, written by Hassan and Rosen, and it consists of two copies of the Einstein-Hilbert action that govern the kinematics of two distinct metric fields, G mu and F mu, that are associated with two different Planck masses, mg and mf. And these interact via this kind of potential, a potential that contains no derivatives, and which is built out of the so-called elementary symmetric polynomials, En here, where beta n are dimensionless parameters. And the argument of the elementary symmetric polynomials is a particular kind of matrix that is constructed out of the square root of G inverse times F, where G and F are the original metrics described by the two Einstein-Hilbert actions.
Sorry, when you say elementary symmetric polynomial, you mean sure polynomials? Is that?
Yes, so the specific order of those, yes, precisely. Okay. So we get traces of this matrix with its, the product of this matrix with itself, different powers of the traces themselves, and so on, up to order 4 specifically. Order 4. Otherwise, okay. you break ghost freedom, as we'll see in a bit.
Okay.
Okay. And so the parameters that we have that enter this action are the 2 Planck masses, as I said, and the 5 in this particular setup are dimensionless parameters beta n. Okay. What is crucial here to notice is that one starts, before one considers the potential, in principle at least, one starts with two separate copies of diffeomorphism invariants, and which are broken to their diagonal subgroup because of the presence of the potential. So this potential breaks the two down to the diagonal copy. It preserves one copy of diffeomorphism invariants. And let's see where it was inspired from. That was from ghost-free massive gravity. So let's go a bit further back. In particular, Fitz and Pauli were the first to write a mass term for a spin-2 field, a helicity 2 field, that propagates around a Minkowski background. Okay, so that is the very well-known Fitz-Pauli-Lagrangian around Minkowski spacetime. It has the linearized Ricci scalar as the kinetic around Minkowski as the kinetic term for the spin-2 field, and also a mass term depending on the trace of h squared and also of h, where h is the spin-2 field squared. And the thing is that this action, to generalize it around nonlinear backgrounds, to promote it to a full nonlinear theory, was notoriously impossible, thought of as being impossible to get. In particular, there was this Bulwer Desert ghost that was associated with all possible extensions around other backgrounds. But Tiram, Kabadadze, and Tolle managed to write a mass term that involves an arbitrary reference metric. So here they wrote this matrix where G is the dynamical metric in their theory, which is governed by an Einstein-Hilbert term. And there is further an arbitrary reference metric F with no kinematics that enters here, and which matrix enters their own elementary symmetric polynomials and gives mass, at least around specific backgrounds, to the metric G. All right. So motivated by this, Hassan and Rosen promoted F to a fully dynamical field and gave it its own Einstein-Hilbert term, as written here, as I described in the context of ghost-free bimetric theory. And now, as far as the degrees of freedom that are propagating are concerned, in Einstein's theory, we have just two, just a massless helicity 2 field. In Fitz-Pauli massive gravity, we have the 5 around Minkowski, so 5 degrees of freedom. And the same is true for the DRGT, the Ram-Kabadadze-Tolle theory around arbitrary backgrounds. And finally, in the case of ghost-free biometric theory, there are 7 degrees of freedom that are propagating in total. Okay. Now notice that these do not necessarily generically split into the degrees of freedom of a massless and of a massive spin-2 field, so 2 plus 5. That is not in general the case. It depends on the background. So around specific backgrounds, those degrees of freedom, those 7 degrees of freedom can split into 2 and 5. All right. Now, in Munich, I started thinking about what we can do from a more fundamental context so as to determine the potential that enters ghost-free biometric theory. So because ghost-free biometric theory is an effective theory, I was thinking, for example, can we embed it in string theory and try to extract information on the structure perhaps of the potential or the parameters or even both that enter the ghost-free biometric potential? And I thought of string scattering amplitudes to do so because those are observables. In general, scattering amplitudes are observables, so they contain a lot of information about a given theory. And this is why we worked on this together with Dieter Lust and Stefan Stübeke and Puri Maslumi. So the plan that we constructed was to first expand in the biometric theory side around specific backgrounds, a theory, because the initial states that we have, the initial fields that we have, G and F, are not well-defined mass eigenstates of the theory, whereas in the string scattering amplitude section, we have to work with states of particular mass. Then as a second step, we had to find appropriate string states and identify them with field theory states we had upon the expansion of the biometric side. And then finally, compute appropriate amplitudes, string amplitudes, that as external legs have those string states. Finally, we were able to construct, as you will see, the effective actions that correspond to the amplitudes we computed. And in the end, we managed to compare them with a biometric theory prediction and decide as to whether there can be embedding and to what extent in string theory. Now, as far as interactions of G and F in the biometric theory side are concerned, the first non-trivial case that appears are cubic interactions, which is why we turn to 3-point amplitudes. So string theory amplitudes involving 3 external legs. Okay, so let's take, so just let me go back. We're going to take these steps step by step in the following, so that you see exactly the process we followed. So first, as I said, G and F are not well-defined mass eigenstates of the theory, so we need to expand. And in particular, we used the very well-known proportional background solution. So in general, these two can be proportional to each other, but we restricted ourselves to the simplest case of Minkowski backgrounds for both metrics. And this is the fluctuations for the respective G and F. And around this Minkowski background, one can diagonalize the mass matrix and determine the mass eigenstates of the theory. By the way, please feel free to interrupt in case there are any questions or points to be made. Anyway, the mass eigenstates take these forms, so they're linear combinations of the fluctuations around Minkowski of the original fields. And at the quadratic level, the actions that describe G and M capital are the following, these two here. So epsilon tilde hat is the so-called Lichnerowitz operator. It is actually the linearized Ricci scalar. It comes from the linearized Ricci scalar around Minkowski spacetime. And so what we see here is that G has the kinematics that a graviton around Minkowski spacetime has. So at quadratic level, this capital G is the graviton. Okay, it should propagate 2 degrees of freedom. Now, moving on to M, we see that it has the same kinematics. This is to be expected because we started with 2 copies of the Einstein-Hilbert action originally. And further, we have a mass term, which is nothing other than the Fierz-Pauli mass term that Fierz-Pauli had first written for helicity spin-2 fields around Minkowski. This should be the case because any other mass term or any other potential in more generically in the context of ghost-free biometric theory excites the bulwark tesseract ghost, or even other unhealthy degrees of freedom. So the structure has to be uniquely this, the one that I give you here. Now, in the Fritz-Pauli case, this mass term is just a parameter. The mass term contains an arbitrary mass parameter, which in the case of ghost-free biometric theory depends, as one should expect, on the biometric theory parameters. So you see here 3 of the original dimensions beta n, and you also see the Planck mass of one of the 2 metrics and the ratio alpha mg over mf of the 2 Planck masses. All right. Now, what is interesting here is that not only do we have the graviton at the quadratic level, but also a massive spin-2 field, which has been put forward as a dark matter candidate. In particular, these authors here suggested that this account for dark matter and studied this phenomenology and managed to restrict its mass so as to match observational constraints. So our motivation for studying ghost-free biometric theory is, I would say,
out of curiosity, do you remember how heavy it has to be to match?
Yes, so it has to be no more than 66 TeV, if I remember correctly.
So yeah. 66. Okay. Thank you.
Right, and I think that was 2016. Yes, I have it here. So meanwhile, I think that this has not changed to become even lower. It has remained so. I mean, I don't think further analysis has constrained this number to further. All right, so I would say that our motivation for studying ghost-free biometric theory is twofold. One is rather formal in the sense that it is unique to describe 2 spin-2 fields. There is no other currently known biometric theory that does not excite ghost degrees of freedom. Of course, there are other modifications of TR that propagate the same amount, like torsion by grad, for example, that propagate the same number of degrees of freedom, but those are not biometric theories. They account for the number of propagating degrees of freedom from torsion and other objects, not a second metric. And the other reason is phenomenological, namely that we have the graviton and also a potential dark matter candidate. All right. So then we moved, let me go back just to check. Yes, perfect. Okay, so we moved then, having seen in the literature the quadratic analysis, we moved on to what was done up to cubic level. So in fact, these authors did expand the generic ghost-free biometric action to cubic order in the fields around proportional backgrounds, and here we restricted ourselves to the Minkowski case. So you see here, let me remind you, G is the graviton, M is the massive spin-2 field. We have very many terms governing their interactions, and their couplings all depend on the parameters that enter the biometric action. Let me also, yes, please.
Sorry to interrupt again.
No, please.
To understand the ghost-free statement, I wanted to understand what you meant by ghosts. Do you mean ghosts in the sense of higher derivative theories of gravity that have the wrong sign of?
Precisely.
Maybe, okay, kinetic term.
Yes.
Okay.
Precisely. So, for example, if you try to write something else here, or maybe even in the simpler case of ghost-free biometric theory, and you calculate the Hamiltonian and the constraints that arise from it, then you get more than 7 propagating degrees of freedom. If you study that extra, for example, if it's an 8, okay, sorry, in massive gravity it's 5. If you study that 6th degree of freedom in massive gravity, then you see that it's kind of an Ostrogasti ghost, namely that its propagator is box square. It appears with a box square in the action, so 1 over p to the 4th in the propagator, which can be thought of as 2 propagators with opposite signs. So the Hamiltonian becomes unbounded from below, and the system is unhealthy. So this kind of ghost is what is avoided by the specific elementary symmetric polynomial structure.
Thank you. That's right.
Thank you. Okay, so we were here. So let me stress, for example, in the case of interactions of one graviton with two massive spin-2 fields. We have interactions in the first line that do not involve derivatives, as you see. Wherever you see bracket, it means trace. We have trace of G interacting with two traces of M, and so on. And in the following, you see derivative interactions. So let's summarize what the authors obtain. These authors obtain up to cubic level. They obtain three kinds of vertices. So cubic self-interactions of the graviton, cubic self-interactions of the massive spin-2 field, and interactions involving one massless and two massive spin-2 fields. The kinetic structure of G and M is strictly of the Ricci scalar, so it comes from the original Einstein-Hilbert actions. Further, the massive spin-2 comes with a no derivative term, but the graviton not, as it should, if it is to be identified with the graviton on the cubic level. And further, GM square involves both no derivative and two derivative interactions. Okay. So also at cubic level, G remains to be the graviton, and its self-interactions are strictly of the GR type. We see that all the couplings that that appear in front of the vertices depend on the parameters of biometric theory in a non-trivial manner. And finally, what is the discriminatory feature of go-through biometric theory is that there is no interaction vertex involving two gravitons and one massive spin-2 field. So the massive spin-2 field cannot decay in gravitons in this theory, at least at cubic level, and actually, as the authors argue, even at higher order. All right. Now, in the string side, how does one compute amplitudes? So basically, let me just say that we want to reproduce from the string vertices like these. We want to see if we can reproduce these vertices from the string. In string theory, to do this, one can calculate amplitudes, scattering amplitudes that in the external legs, as I said, involve string states. And this is done by mapping these states to the so-called vertex operators. And these operators are conformal fields that have to satisfy specific conditions due to BRST invariants. And those are nothing other than the mass being on shell. So each leg has to be on shell, satisfying the on shell mass condition. And also these fields in the external legs have to be transverse and traceless. So since the vertex operators are transverse and traceless and on shell, have on shell mass, namely are on shell, as we will refer to all these conditions in the following. The full amplitudes we will calculate are going to be on shell. Okay, this means that we can only determine a subset of these vertices that I showed to you here, these terms that correspond to the GM square vertex that I showed to you here. Because here you see more general things. You see things that are not necessarily transverse or traceless or satisfy the on-shell mass condition. So somehow we have to bring the two in a comparable form. And how do we do this? By imposing the on-shell conditions at the level of the fields. So bringing their equations of motion to the form that the respective fields are on shell. So how is this done? The graviton in particular has to satisfy the massless Klein-Gordon equation, and further gauge invariance can be used to set it to be transverse and traceless. In the end, leaving two propagating degrees of freedom as it should. And further, the massive spin-2 field has to satisfy the massive Klein-Gordon equation. And also, if its original equation of motion that comes from the Litherowitz operator and the Fitz-Pauli mass term is to be brought to this massive Klein-Gordon equation, then also these constraints, now not gauge choices, have to be satisfied. Okay, so these set of equations now leave the propagating number of degrees of freedom to 5. Okay, so we know that these are by default imposed on the string side if we want to calculate on-shell amplitudes, which is exactly what we're going to do. Thus, we need to impose them also in the field theory side. So these equations, we will impose all of them to the cubic vertices I showed to you, I referred to in the previous slides. And in fact, this simplifies the situation a lot. So remember I showed to you a whole page of terms. Now this whole page becomes just these two lines. And we lose several terms because of the on-shell conditions, but still there is information from the bimetric structure that remains. In particular, in the case of the self-interactions of the massive spin-2 field, you see that in a very particular combination, the two of the dimensionless beta parameters enter. All right. Now, we see that we have only these four parameters that enter, one of the two Planck masses, the Planck mass ratio, and two, as I said, dimensionless parameters, the beta n parameters. Because of the on-shell conditions further, only terms involving the trace of m, traces of m cube actually survive. So as you see here, the GM square interactions are only involving derivatives in this case. All interactions that do not involve derivatives disappear because of the on-shell conditions. And further, if you look closely, then you see that all these terms that I gave in the previous slide are all possible Lorentz invariant terms that one can write with on-shell fields, so transverse and traceless rank 2 tensors. Okay, after partial.
Sorry, do I understand that you have a free parameter as well in beta 2 is not determined? Any value of beta 2 would be
That's correct. Right now it is not, but then again, there is a condition on the cosmological constant. So this I do not, you can look at it in the paper, I do not give it here, but in fact you can compute around these backgrounds the cosmological constant, and there's two, one corresponding to G and one corresponding to F, and you have to impose that those are equal. So you get a further constraint from there, and also we need to impose that they're set to 0 because we're considering Minkowski. Why should they be equal? Because G and F satisfy their equations of motion look very much the same, and they're just the copies of the Einstein-Hilbert action up to the mass term. So we get a further constraint because of that, because of the cosmological constant and the fact that we're in Minkowski space-time.
Can I ask a question?
Please, yes.
It seems, if I understand correctly, the only signal of a bimetric gravity is the coefficients, which are uniquely fixed.
Sorry, I couldn't hear.
How do I know this is bimetric gravity? I only know it from the coupling constants and the relations. Okay.
Yes.
So
yes.
my question is, why are these relations preserved by renormalization under renormalization? Why are they stable?
Okay, very good. So two things. So what is unique in this structure is first, as you say, as you very well point out, the parameters, exactly how the parameters enter the couplings. Second, the absence of a G square M term, so a term that involves two gravitons and one M. Now, as far as renormalization is concerned, this theory is an effective field theory, and it's not renormalizable, much like GR is not. So we're not aiming at proving anything about its renormalizability right now. We know that it cannot be. We just want to try to extract information from low energy string theory expansions and see whether it can be embedded in a more fundamental context where, in fact, gravity can be thought of as being quantum.
Could I not have derived this by starting, without forgetting about string theory, by just checking the coefficients so that I get ghost free theory up to this order?
Very good. Absolutely. Absolutely. The thing is, you would also get G square M terms. I'm not sure as to whether this is excluded precisely of ghost freedom, because there's also the constraint of having one diffeomorphism invariant. So this one has to check. But certainly, if one would want then to generalize around to all orders and around generic backgrounds, starting from the cubic order, this would be very, very hard. So I wouldn't know how, given this, one would get the elementary symmetric polynomial structure in a ghost-free manner.
Okay.
All right. Yes. So
Yeah, so I have one further question. Since you just wrote down a cubic term and for M cube, so if you use your extra field as a dark matter candidate, then probably you can't afford too much self-interaction because we would see that in the dark matter. So, do you adjust your betas to have a very small M cube term? Or?
I think not. This is a good question. So I think they were not constrained in the analysis, but I have to look that up. So to some extent, I think they were kept. Let me try to remember. I think the only constraint was put in the end on the mass. So the combination of the beta parameters, not to each of these independently. But I can look it up again if you'd like.
Okay, thank you.
All right. Yes, we were here. So again, if you look at these kinds of terms, these kinds of cubic interactions, as I was saying before, they're in fact all possible Lorentz invariant terms that you can write with on-shell fields, transverse and traceless, massless, and massive rank 2 tensors, up to partial integrations, of course, and this excluding this G square M interaction that is not there by construction in ghost-free biometric theory. So as I'd like to point out, the terms themselves are not unique to ghost-free biometric theory, but the particular coefficients and couplings are, which is why we'll move on to the string. Also because in the context of string theory, never has it been had it been calculated in the literature before. Those kinds of amplitudes, I mean, had never been calculated before. So we do not know exactly what the string will tell us about the low-energy interactions of masses and massive spin 2 fields, because nobody did that before. So let's move on to the string.
I have one more, sorry.
Please, yes.
With this choice of the coupling constants, does one find any new symmetry of the system or something new, okay?
Sorry, I couldn't catch the first part of the sentence, sorry.
The only uniqueness about this model is the choice of the coefficients in the Lagrangian. So
yeah,
this give additional constants of motion or something like that, okay? Something characteristic of the model or some inequalities for the energy, okay?
I see what you mean. First of all, I think it's because it's the truncation to cubic order that we have lost part of its uniqueness, okay? But there still remains the absence of G square M, which is still quite a lot. It's saying quite a lot about the theory. But then again, if one goes to higher orders, then perhaps further manifestations of its uniqueness may appear. Now, as far as energy, saying inequalities are concerned, not that I know of. I think that the Hamiltonian has been studied extensively to show ghost freedom, so in a series of papers actually. But from the point of view of one calculating the number of constraints so as to guarantee that the number of propagating degrees of freedom are healthy and the ones that they should be, I don't know of any inequalities. Maybe it has been done. I have to look it up.
Okay. All right. But you have a full action to begin with. You don't have to look for cubic order or anything. You can go back to your original action and ask for solutions to those equations. Have people looked at those?
Yes. So actually the whole spectrum of biometric theory, they have also black hole solutions, anything that you can imagine, they have looked at. And there's actually a lot of its, all of GR solutions that you can think of, they're part of the biometric theory spectrum. But there's further more exotic, like exotic black hole solutions that are not part of GR. And
yeah, it looks natural that because one can always set F to be the flat metric, and you're going to reduce it to GR, and those have to be solutions, presumably. But there's a question of stability. Is that flat? Is F being flat a stable solution to those?
No, so sorry, I want to
look at small fluctuations around it. Sorry.
Let me say, Dejo, that is related to the question of, is the Hamiltonian bounded below?
Well, it's the Hamiltonian for such a diffeomorphism invariant theory is probably 0, so I'm not quite sure what
No,
that's the right way of
the
looking
ADM
at it.
Hamiltonian, the ADM Hamiltonian. So it is a like in the Schoen-Yao proof, okay, or Witten proof.
Yes.
There is a Hamiltonian. There is an
Yes,
energy.
absolutely, absolutely.
But
Yes,
It's like mountain below.
I could look at, for instance, a Schwarzschild solution here and look at small fluctuations of F to see if they were negative modes to indicate that it was unstable. That's the
Yes,
type of analysis that one would do.
but now are we talking about stability of solutions or stability of the generic Hamiltonian? Because
Stability of solutions.
okay, but that's a different thing, because I mean the Hamiltonian, you can write it as Ayala very well pointed out in ADM. Actually, that's exactly how you one shows ghost freedom. You write it in ADM variables, and then you have to analyze the constraints. Now, stability of solutions is another thing. Of course, the GR part is stable, but no matter what those extra solutions are, the thing is that the ghost-free biometric theory is not, at least currently, it is perfectly well observationally allowed. So even though there's more solutions, that some of which may be even stable, one has to.
Well, what I'm thinking of is the type of situation where in the Einstein universe, which is a static universe with S3 cross time, if you look at fluctuations, it's unstable, so it's dynamically unstable. You could have a dynamical instability of Schwarzschild due to the presence of this F. I'm just wondering if people have checked that those instabilities are absent.
I think so. I think so. The thing is, because I personally care about its phenomenological aspect, and that is restricted to that part of its spectrum that matches GR, because up to now we know that GR observationally is a great theory. I have not looked at those theories, but I know very well, and I can give you the references, that all possible solutions have been studied. So,
okay.
And to the extent that they know exactly which are exotic ones, which are the GR ones. The important thing here is that for a large part of the parameter space, this theory resembles GR very much.
Yeah.
GR and another massive spin 2 field that interacts with it.
I see that. Sorry for the interruption.
No, please, no problem. Let me just go to the string part because time is running short. Okay, so as I was saying, we're going to go to string amplitudes now. And the question that raises itself first is how we identify the massive spin 2 field with which state we identified from the string perspective. So the Graviton we very well know, as I explained, it's a closed string state, there is no doubt. But the massive spin 2, in principle at least, it can be closed or open. And in fact, drawing motivation from work by Ferrara, Quejas, and Lust, we identified with an open string state. Why? Because in that work, what they did was to consider the first massive state in open type 2B string theory, and actually identified with the massive mode that appears in Weil square supergravity, I mean, in the effective Lagrangian description. Which I should highlight is a ghost in that theory, not a healthy degree freedom as in our case. Anyways, drawing motivation from that, we identify our massive spin 2 with an open string state. The first massive open string state that appears in type 2B string theory, and which is constructed out of these kinds of states, which involve the fermionic and bosonic transverse oscillators acting on the vacuum. Okay, and the combination of these two states yields in the critical dimension the correct number of the propagating degrees of freedom that correspond to a massive spin 2 state, with a mass that is 1 over alpha prime being the string scale. So if we choose to identify our field massive spin 2 from the field theory side with the with this string state, we're forced to make further this kind of identification. So you see here, I have the Fritz-Pauli mass square as predicted by the at the quadratic level by the ghost-free bimetric theory.
Sorry,
Yeah.
why
Yes,
is this a boson rather than a Fermi? It looks.
Which one?
You've written
Here?
this state with a mixture of fermionic and bosonic, and it looks fermionic. It looks like it should be a fermion.
Okay, one second. These are the oscillators that act on the vacuum, and these have specific weights that have to that add up to be 3/2, so as to correspond to the level 1/alpha prime. Now, how do you construct states out of these? How do you construct the degrees of freedom out of this? You need to count the transverse modes that propagate in this combination here and these combinations here. The corresponding vertex operator will contain both fermionic and bosonic fields. They're respective to these. So we're going to have a x mu space-time world-sheet coordinate x mu and psi mu from here. But these are on the, am I saying it correctly? On the world-sheet. So they are space-time bosons. That's the thing. They're world-sheet super partners, but space-time bosons. So indeed, we'll construct a boson out of this.
Okay, thank you. Yeah.
All right. So because of the identification we make, we are forced to relate the Fritz-Pauli mass with the 1/alpha prime, namely the biometric theory parameters from one side with the string scale in the other side. Now, we're currently analyzing further possibilities, namely whether the massive spin-2 field may be a closed string state, for which we actually have already a lot of evidence, as you will see in the rest of the talk, and as we have been seeing already from our analysis, our preliminary analysis. Okay, so now how does one calculate an amplitude at tree level if one has to deal with these kinds of states? And the simplest case of amplitudes, of string amplitudes that involve both open and closed string states, is that of that has a topology of the disk. And in that case, the generic expression is given here in these references, and basically tells you that the amplitude is nothing other than the correlation function, the integral over all possible worldsheet insertions of vertex operators of the correlation function that involves normal ordered vertex operator, each of which corresponds to the external legs of our scattering amplitude. Okay. Now, several cases of this were considered and studied by Klebanov, Torlasius, Gupse, Hashimoto, and collaborators in the late 90s. But in all these cases, the external states were massless. And in fact, it was not until 2010 where Feng, Lust, Schlotter, Stiebecker, and Taylor considered the case of one massive external state and all the other being massless. So our novelty consists in two aspects. First, that all external states that we're considering are either helicity 2 or spin 2 fields, so all are rank 2 tensors. And further, that at least 2 of the external states we use are massive. And these two aspects complicate and further make interesting the calculation of the amplitudes and further the extraction of the effective actions. All right, so in the case of the superstring, the Graviton vertex operator is given by this expression here. So it's basically a conformal field that depends on the worldsheet points of insertions in the disk of the respective of this operator, and also on its polarization, on the polarization tensor and momentum that the state is thought of as having. And you see here the x mu and psi mu, the worldsheet fields, whether space-time bosons I mentioned before. And so you construct this kind of object that has to satisfy the so-called on-shell conditions that I mentioned before. So transversality, masslessness, symmetry, that it's a symmetric representation of the Lorentz group, and further tracelessness. Okay, So this is the graviton here. It's the graviton vertex operator we're going to use. Whenever we see graviton in the external leg, we use this respective operator inside the correlation function. And further, in the case of a type 2b open superstring that I showed to you before, the two states I showed to you before, give rise to this kind of vertex operator, where now you see the worldsheet point of insertion here, and also its polarization tensor and momentum. Further, the fact is that there is a sort of degeneracy as far as vertex operators are concerned, in the sense that they can be written in different superghost pictures, the reparameterization superghost on the disk. And so the very same state can be described by a different vertex operator. One can write infinitely many, and one can use any of these inside the correlation function or inside the amplitude, as long as the condition that the sum of the respective ghost pictures on the disk is 2, so that it cancels the background charge of the disk. -2, excuse me, -2, so that it cancels the 2 of the disk. All right, so in these references, both pictures were constructed here, and we're going to need both of them so as to be able to write an amplitude that involves interaction of a massless G and 2 massive spin and 2 fields M, such that the total charge is -2. And further, you see here the on-shell conditions that I give for the massive spin-2 field, that are the ones that should be expected by now, given what I said. So transversality, the on-shell mass condition, the symmetry property, and also tracelessness. So we have our tools now, and we can start writing and computing string amplitudes. So in particular, the case of 2 massive spin-2 and 1 G, the GM square interaction I showed to you, is computed by calculating this kind of correlation function, which is exactly what we did. So you see here 2 vertex operators for M, 1 for G. Okay. Now, in the momentum, the form of momentum conservation in this particular case takes this form. In particular, whenever you see K corresponds to an open string state, so K1 and K2 correspond to M, and Q corresponds to closed string state, so to the graviton. But because the brain is thought of as being super heavy, only conservation along its direction is thought of as being meaningful. So there is a way to consider that component of the closed string momentum working with a so-called D matrix, a matrix that contains all the boundary information, so that the projections along and transfer to the brain can be computed. And so this is the kind of conservation we use. And further, even though it's a 3-point amplitude, one can define Mandelstam variables by considering this, by making use of this D matrix here. And in fact, working as if it's a 4-point amplitude, both as far as the kinematics are concerned, and also as far as the contractions inside the correlation function are performed. Okay, so we define here these kinds of 3 SDU Mandelstam variables. And in fact, using momentum conservation and the on-shell conditions, we can show, as was shown also in the massless case, that there's a single kinematic invariant, which in our case takes this particular form. There's a constant in front, and this product of open string momentum in the second term. All right. So we start really by using, let me go back. We substitute inside this correlation function the exact expressions that I showed to you before, all of the vertex operators that involve x mu and psi mu, the 2 kinds of worldsheet superpartners, and start performing contractions using Griggs theorem and also the disk correlators of these fields that are very well known, inside this big correlation function. And we will perform all these contractions and gather all possible terms that we can. And in particular, we have to also use some technicalities here, namely fix 3 vertex operator positions, insert C ghost. We can discuss it if you want in the end. All right, in the end, we bring the full GM squared amplitude to the form of an integral over the real line that we package for convenience in this form here. You see, it is a sum of 4 kinds of terms where the index I refers to the power to which x1 minus x2, with x1 and x2 being the open string vertex operator insertions, the power of this that appears in the denominator. So for example, A4 that I give here corresponds to terms that come after the contraction with 1 over x1 minus x2 to the 4th. I repeat, x1 and x2 are the open string vertex operator insertions. Okay, and because these expressions are very lengthy of A4 and so on, I give you here just the simplest example. It is, as I said, an integral over the real line, where x is the real line parameter. Excuse me. You see here the 3 polarization tensors, corresponding to the external states, and further you see the exact x dependence on the worldsheet of the integral, and several kinds of A, B, C, delta, E, and F objects with indices that arise, that are the so-called, we refer to them as the kinematic packages, and that arise because of the numerators of the contractions. And they depend on the momenta, as you see here. I give you again the simplest example because they're quite lengthy in the formula. They depend on the momenta Q, K1, and K2, the matrix D, and also their exact expansions in alpha prime, expressions of alpha prime. So we have actually organized them in different powers of alpha prime, so alpha prime squared, and alpha prime cube. And in fact, for all kinematic packages, these 3 kinds are the only powers of alpha prime that it appears in. And they're not truncations, they're the full exact expressions that we have obtained after performing the contractions. Okay,
And
we have also.
S is one of the Mendelssohn variables, is it?
Which one?
You've in parameter S in there. It's presumably one of the Mendelssohn variables.
Here you mean, absolutely,
Yeah.
yes. So exactly.
And you've just picked it out as an example, presumably that you.
Very good. Yes, we could have very well chosen another one of the 3, but there's just one of the 3 that is independent, so we can equally well choose whichever we want. Okay. All right. So this is basically what I said. The 36 kinematic packages we have computed, and I gave you just one example here. And further, by performing extensive partial functioning and evaluating the real line integrals, we bring, for example, a form to this form, which is now, it contains a dependence on the kinematic packages that contains dependence on more than one of the original kinematic packages. As you see here, the E that enters here depends on E with indices and B with indices. And further, what you see is gamma functions, so products and ratios, fractions of gamma functions that depend on S, as Danger is pointing out. Okay, so schematically, our amplitude is something like a product that depends on a kinematic object that depends on the momenta and alpha prime, and another object that depends on the Mendelssohn parameter S, and which arises because of partially because of the contractions, the so-called Copan-Nielsen function that I can refer to in the end if you'd like, and in fact the integral. So this contains the result of the integral, the dependence through the gamma functions on S. Okay, we have, by the way, computed the full amplitude that corresponds to GM squared, which is valid in both the critical dimension and in 4 dimensions, and for any deep brain dimension.
Sorry, I had to ask, may I ask? There appear to be poles in the amplitude in the variable S.
Sorry?
What is it? There appear to be poles from the zeros or the poles and zeros. What are they? I mean, it's, the analyticity property of A4.
Yeah, okay, so the thing is, from this structure, it's very hard to say because we have very many terms. We don't, we need to sum them, right, to have the full amplitude, and we have different kinds of terms that, for example, the poles of this here, it does not tell me that these are the poles of the amplitude itself. So I cannot answer that question. You see what I'm saying? Because the full amplitude is a sum of these terms and all the other A's.
Yes.
We
There
can
are
only,
both zeros and poles. Okay.
yes, true,
Pendulum,
both.
yeah.
True, both, absolutely, yes. What we can do, and what we did, was to expand in the low energy limit, but in general, one can also consider other values of parameter ranges of S, and there perhaps you can be able to extract more information on the poles, but only in the specific ranges of S. Okay, let me move on to the M cube. So the scattering amplitude corresponds to the scattering of 3 massive spin-2 fields that we computed in a very similar fashion. And this is our result. This is our full result. It's not a result of a truncation, neither an expansion. This is the complete amplitude. And what you see here is that if one is to compare with a biometric side, there is already a problem. And what is that? The first line is a no derivative line. The second, no momenta, let me say here, because we're in the amplitude picture. The second and third line, they contain 2 momenta, and then you have 4 momenta terms. These 2 momentum terms, their structure is precisely the same as the structure of the 3 graviton amplitude universally in string theory. Okay, and the low energy. Sorry, not in the low energy, in the at 3 level. So, and we know that M cube, so M at cubic level is governed by the Einstein-Hilbert term. So it has to be like the graviton. And the only difference that we see between our result and the graviton amplitude is that these prefactors that I give in 3, that we have for the massive spin-2 field, that I give in yellow, in orange, they are actually a 2 in the case of the graviton. So instead of a 3 in these 3 terms, we have a 2. Already we see that we're not going to match. We're not going to match the graviton, we're not going to match biometric theory. Let me just point out that this was a simpler calculation in the sense that there was no integral after inserting the C-coast, but anyways, it becomes more of a technicality. I can refer to that in the end. Okay, so we have our 2 amplitudes, our full amplitudes, and we're now able to extract the effective actions at lower energies from these. And to this end, we make 2 simplifications. The first is that we restrict the D matrix to the simple identity matrix value here. So that D with 2 indices alpha is nothing other than the Minkowski metric. And also we assume that the gauge group on the brain is only U1, so not the generic non-BDM case. And further, to extract the effective actions, we make these replacements. So we substitute the polarization tensors with the respective fields and the momenta with the partial derivative that acts on the respective field. Okay. Now, for GM square, to extract the effective action is a subtle process. In what sense? If you remember, we had written everything in terms of S, okay, which contains this object here, alpha prime, K1, K2. Alpha prime, I remind you, is the string scale. K1, K2, the open string momenta, with K1 square and K2 square being equal to 1 over alpha prime, okay? Because they satisfy the on-shell mass condition. So this object, alpha prime, K1 dot K2, for small values of alpha prime, goes to 1. It becomes dangerous at low values of alpha prime. Whereas if you consider this object where Q is the closed string momentum with Q squared being equal to 0, you get a fine, a well-behaved object even at very small values of alpha prime. Okay, this means that if we extract, if we first extract the effective action and then substitute via S from this relation, and then perform some kind of truncation to the order we want to match biometric theory, the truncation will contain terms that depend on these dangerous objects here, and this is something we want to avoid. Okay, so a substitution of S after a before a truncation and then a truncation to that action is not meaningful. This is why we actually perform momentum conservation in S, writing in terms of 1 open string momentum and 1 closed string momentum, and then expand the, remember that the whole amplitude is given by kinematics times integral, And so we expand the integrals in a small value of s, and then substitute using this relation, which is very much well behaved. Also, we simplify the object's kinematic packages for these two, in the previous slide, these two cases that we restrict ourselves in. And then we consider the product of the two and keep terms only up to order alpha prime square. Okay, so this is the at low energies, at low values of alpha prime, the amplitude describing the interaction of one graviton in two massive spin-2 fields up to two derivatives, up to two momenta in this case. All right. Right. So now we extract, making the replacements I told you, the polarization tensors and momenta, we extract the effective actions up to second order derivatives. And for the graviton cubic order, we get this action, and for GM square, we get this. All right. So now we compare with the bimetric side, and if you remember, I can also go back in the slides if you ask me, the structure is precisely the same. All coefficients match if one further sets that the closed string coupling is equal to the coupling that is predicted in the bimetric theory side. So this is exactly what we have in front in the respective bimetric theory cases. So the question is, can we really do that? Because as I told you, we have hints already that M cube does not match the two sides, field and string theory side. So then, that's why we moved on to M cube and considered and extracted again its action from the respective amplitude, which is this action up to fourth order in derivatives. And you see here a 3 instead of a 2 that is in the case of the graviton. And instead of a 2, if I go back just to convince you, just a few slides, to the bimetric theory action, you see, in M cube, this is a 2. The derivative terms of G and M at cubic order also are precisely the same. Only the non-derivative terms are different. And they're precisely the same, and they're both determined by the Einstein-Hilbert action, the linearized reaching around Minkowski. Okay, so we see here, let me go to our result. We see that we get this 3, we check this several times, and it does not match the bimetric theory prediction. Okay, so what does all this tell us? First, let me remind you that we have the full amplitudes for both GM square and M cube, and these are they don't, in our general results, they don't depend on specific values of dimension. They're valid in the critical dimension, not just in the 4-dimensional space. And the bimetric theory is thought of as making sense. Further, they are valid for generic values of the D matrix, and so one may consider other kinds of brane configurations. And now, what about our results? In the case of GM square and also the graviton, we found perfect, if you want, agreement between the string and bimetric prediction. However, in the case of M, we find that all terms match up to that 3, which means that the quadratic kinematics of the massive spin-2 field that comes from the open string spectrum is not GR-like, okay? We refer to this as the 2 versus 3 discrepancy, because remember, 2 is the GR prediction and also bimetric theory prediction, or if you want, assumption, because one chooses to work in this theory. We get a 3 in our own case, so it's a 2 versus 3 discrepancy. And in fact, one cannot help but be reminded by the so-called Van Dam-Veltman-Zakharov discontinuity, in a particular manifestation of which there is a 1/2 versus 1/3 discrepancy. And what is that? Let us consider the Fritz-Pauli, the massive spin-2 propagator. Now it's field theory, let me remind you. In the limit of small Fritz-Pauli mass, it takes this particular form and up to singular terms. The rest of the terms match precisely the terms of the graviton if it weren't for this 1/3. In the case of the graviton, it's a 1/2. So we get a very similar discrepancy, but beware, this is a very different, this is qualitatively very different from our case. In our case, we get a discrepancy because the kinematics are different, for the massive spin 2 of bimetric and the massive spin 2 of the open string spectrum. But here in the Van Dam-Bellman-Zakharov, the discrepancy is due to the mass term of the Fitz-Pauli massive spin 2 field. Okay. So what we gather from all our analysis is that the open string massive spin 2 state is not a suitable candidate for the massive spin 2 field that goes through bimetric theory accommodates. And currently we're investigating other possibilities, for example, the case of the closed string spectrum. So thank you very much.
Thank you, that was excellent. Thank you for a nice introduction. Questions, it's open to questions.
Well, thank you again. One question I have for the decay of the M particle to graviton. You said there is no G M term, and then you started to say something about G cube M and higher powers of G, but I didn't catch that.
Oh, no, I meant that at cubic order, there is no such channel, G square M.
Yes.
Also in the string side, we only compute G M square.
Yes.
That's what I meant. And
do you know anything about G cube M?
You mean, so now not just 3 legs, but 4-point amplitudes.
Exactly, an M particle. Yes.
Okay, so if you look at our paper also, you'll see that the calculation is very technical and very lengthy. So I presume that the 4-point computation is going to be even more lengthy. And we already got enough information so as to decide as to whether this state is suitable for bimetric theory or not, which is why we didn't move on to 4-point amplitudes. But this is a very valid question, absolutely.
Okay. So essentially for quantitative reasons, it would not matter for the age of the universe. But
it wouldn't matter for our own analysis, in the sense that now we know that it is not an open string state, but maybe it yields some other very interesting information that I cannot exclude right now.
Okay, thank you.
Other questions? I mean, it is surprisingly close to such a state that a factor of 3 versus 2 is very surprising to me.
Yes, yes. And in fact, it is so surprising that we, for a long time, we did it again, just to be sure that we did the right thing. What I can say is that the 2 is associated with the assumption that you start with 2 diffeomorphism invariances in the field theory side. In the string side, however, what we discover is that the open string state is not associated with diffeomorphism invariance. And in fact, a priori, we couldn't have known. We didn't know if this state supports another copy of diffeomorphism invariance. Right. So this 3 is surprising, but then again, it is not excluded by any other considerations in the context of string theory. String theory doesn't tell you that all massive spin 2 fields that appear in the towers have to be associated with diffeom invariances.
Is there a reason you would expect a second copy of diffeomorphism invariance in the string setting?
In the open string sector, I suppose not, especially after our results in analysis. But in the closed string sector, I cannot exclude it. And in fact, if you ask me personally, I would expect it even. Because
why
the Graviton. Excuse me?
Why would you expect it?
Maybe expect is not, I should have used a different word. I only mean that we know that the Graviton is a bulk field. So we know that diffeos are associated with a bulk. Okay, and not with strings. So if we are to find another copy of diffeom invariance, intuitively, I am saying that I expect that to be in the bulk, but I'm not saying that I have to find that or that we will find it or anything like that necessarily. We might, but I cannot say this at the moment. That's all I'm saying.
The other question I have is that the string case is supersymmetric. So I would have expected to get a supergravity out of this. And I would expect to get a second spin 3 halves field. Is there
All
some
right.
reason to believe there is?
All right. So we didn't consider, okay, why did we start with a superstring? In fact, we repeated the computation for the, as you can see in the paper, for the case of the bosonic string for M cube, just to check that the 3 is fine. And in fact, it's a 4, by the way, instead of the 3. Anyway, why did we start with a superstring? Because it avoids the tachyon that is part of the bosonic strings. That was the only motivation. Now, we considered bosonic states built out of worksheet superpartners, but we didn't consider their space-time superpartners. So I cannot tell you what happens to the superpartner, the Gravitino, or the superpartner of the massive spin 2 field in this theory. This is something additional that remains to be done if one has the interest and motivation.
Which your calculation was using fermionic degrees of freedom intrinsically,
Yes.
so it relied on the supersymmetry, on the supersymmetric case.
I can see why you say this, and I agree. Yes, yes. In that sense, it totally relies. Yes, but if you want, let me make this statement precise. The interactions of the 2 fields that we compute are valid up to the assumption that those have superpartners, as you very well point out, Denjo. Yes, but we have not considered their own interactions in scattering amplitudes.
But it might be, I mean, is there a reason to look maybe at the purely bosonic one and try and identify
Yes, why not? As I said, the only motivation for not going there is the tachyon. But then again, for M, we did it because we wanted to be sure for the 3. And there we found a 4. Okay? So not even the open bosonic string state, open string state in bosonic string theory doesn't work.
Yeah.
Okay?
Can I ask, what is the bound on the mass of the spin 2 field?
So I think it's 66 TeV. It should be less than 66 TeV.
66. So let me ask a question. How does one experimentally distinguish this model from any other model? What is the signal?
You mean ghost-free biometric theory?
No. Yeah. Suppose you say this is a theory. What should the experimental CMB spectrum, whatever, what should they do?
Yes. What I can tell you is that, okay, you mean with respect to other dark matter models?
And there are so many models. So also these 2 factors of 2 and 3, how do they affect phenomenology?
Or the 3, you mean?
How do I know this model as, how does it
I think he's focused on your original, your first transparency where you wrote down the action.
Yes.
For example,
one can just take that and say, okay, this is a nice theory. How would I find a signal for the second graviton? Yeah.
Okay, yeah, I see what you mean. The point is that this massive spin 2, okay, suppose you start with this theory and you couple it to matter, okay? Now, one restriction for that coupling is that only one of the 2 original metrics couples to matter, either G or F, with no loss of generality, which one you choose, because otherwise you excite the ghost. I mean, you can show this again. So you choose one of the 2, and then you do the mass eigenstate diagonalization. And what you see is that the massive spin 2 field interacts only gravitationally. Okay, so it couples to G, and it couples with a suppressed coupling to T mu, the energy momentum tensor. And so it satisfies the fundamental dark matter property in the sense that it's only seen by its gravitational interactions. Now, yes.
I mean, I was going back to Bernard's question. Then is, well, why is it stable to? Why doesn't it decay into gravitons immediately, just like some other particle would decay into photons? You might get
Okay, so it doesn't decay into gravitons using a G square M channel, but other channels where you have in the propagator a standard model particle, for example, are not excluded, and in fact they're very well expected. So it can decay into gravitons if there's a mediator. That's my point.
By the way, the talk was quite good. I enjoyed it. So,
Thank
but
you.
I want to ask more questions.
Please.
Please, we're in no rush, Val. We like to continue. So I hope you don't need to rush off. We tend to
No.
I have to leave
run
soon,
way
but
over time.
in any case,
No. Please go ahead.
will it affect, this is string 2 and couples gravitationally. So will it absorb affect the polarization of the signals we are getting in CMB? It is string 2. So, and the
Yes, I have to.
model.
Excuse me.
Sorry. If I get polarized, and CMB has some polarization. So I'm asking whether there will be some signals or effects on the experimentally observed polarization in the CMB.
Okay, that's a good question. I don't think I can tell you more than the fact that what I saw in these papers and what I remember is that it is not excluded that the massive spin 2 field is account for that matter, but I don't know. From what I understood, it's compatible also with the CMB, but I have to look up the references more thoroughly. You see, our paper was a string theory paper, and we dealt with the field theory side to the extent that we brought it to a form that is comparable.
Okay.
So our focus was the string theory computation.
Okay.
That's fine. We appreciate that. It's just we're not familiar with these series.
No, sure.
We're trying to be educated. We're picking your brain as well.
No, it was well meant. I very much appreciate also the discussion and comments and questions. Absolutely. So.
But I mean, this action is surprisingly simple to me. Wow.
Simple.
It actually doesn't even look that ugly. So,
I guess you can say that.
Biometric theory.
Yes, I mean, if you expand, you get so you get products of, like, for example, in the Philippine formalism, you have E tilde E times E tilde times E times E tilde. So it looks a bit more peculiar. But yes, this is a compact form where.
But you have written it in terms of very nice symmetric polynomials, which look looks like a natural way of writing it. When you're telling us that the expression in terms of these symmetric polynomials with these parameters, 4 parameters, it comes out from the demand of ghost freeness, which is curious.
Yes, but yes, that's what I said, and exactly. But I don't think historically it came out in this linear form. Like, people started with elementary symmetric polynomials and then showed that because of this, straightforwardly you get to ghost freedom. It happened historically in a very different line of thought. So initially, okay, it was first Fitz-Pauli and then Bulwer and Desser who came up with this no-go theorem that you cannot generalize the Fitz-Pauli action, and they considered arbitrary backgrounds in general. So all nonlinear cases, they considered brought the ghost back. But then I think it was well, there was the paper also by Arkani Hamed and Georgi and Schwartz, where they did the longitudinal Goldstone mode analysis of massive spin 2 fields. And then there was also the DGP model, Dvali Kabadadze Tolle, so sorry, not Tolle, Porati, where they, for the first time, they managed to write, to construct a brain world model where you could have a massive spin 2 resonance, but not, it was a resonance. It was not in the spectral representation, not mass term in the field theory senses in here. And then Deram Kabadadze Tolle came, and they started with the construction, if I remember correctly, from 5 dimensions. So, and like writing a mass term in 5 dimensions and doing the truncation to 4, and then they started to see the square root appearing, and then the repackaging in the elementary polynomials. But also the proof of ghost freedom was not done in one paper. Initially, for ghost-free biometric theory was only argued to be the case in a particular decoupling limit, and then further were several papers, and then it came ghost-free biometric theory, where and then more papers that argued in favor.
Just for clarity, your computation was in flat 10-dimensional space. You were using this action. Is that correct?
Yeah. So for a generic metric in 10 dimensions.
Yeah.
And then we try, yes, and then we go to Minkowski 4D. Yes. because in fact, in a very straightforward manner, because the form of the states and the vertex operators that we use, the Graviton and the massive spin-2 field, they're very much the same in the critical dimension and in fourth space-time dimensions.
So in fact, you took a Kaluza-Klein reduction or something like that?
No, that's what I'm saying. We didn't even have to do a Kaluza-Klein. The exact same vertex operator is valid in 10D and in 4D. Okay. And so the exact same amplitude is valid in 10D and in 4D.
But in the string context, don't you have to give some argument as to what's going on with the rest of the six-dimensional space?
Yes, and in fact, those form you get a different. Okay, now comes supersymmetry, as you very well pointed out, Dendro, into play. So you start with some multiplet in 10 dimensions, and those extra fields that you mentioned, so they're scalars, if I remember correctly, 6, they become further super partners in 4 dimensions of this massive spin-2 state that we use.
Okay. Oh, yeah.
So when we go to 4D, supersymmetry increases, more super partners appear in the same multiplet. No.
Chrysoula, I have to leave. Okay. Yes. But very good talk.
That was
next time we'll see. Okay. Bye.
Thank you so much for attending and for your questions.
Thank you.
Okay.
Excellent.
Fine.
Are there other questions?
I have a question.
Yeah, Gian Domenico, sorry. One.
So there are a lot of efforts nowadays to understand also Lorentz-broken gravity from the phenomenological point of view. You know, there are applications also in condensed matter physics or, you know, generic. And I know also there is a trend in string theory to start thinking about the Lorentz-broken string theory, like Niels Obers from Eigen Institute. So I was just wondering if you can have somehow a sort of a connection between Lorentz-broken gravity, Lorentz-broken theories.
I see. Yes, that's a great question. I don't know. I mean, I'm aware of the work by Niels Obers and collaborators. I mean, in Denmark and also, I think also in Switzerland. I think there was some. Anyway, I'm aware of that. I don't know of a connection. Also, our case, even the string theory case, breaks diffeolus, not Lorentz invariants. All right. So I'm guessing that you cannot directly relate what we're doing or even biometric theory to those theories, but those are very much interesting in their own right, absolutely.
And in the case also of torsion, suppose that you also relax the Levi-Civita condition.
Yeah.
I mean, I guess that this bimetric theory would be a little bit more general. I mean, there should have been some extra terms with two independent, let's say, dry binds. I mean, the first order formula, not the second order.
Yeah. You mean to ghost ray biometric theory do that, to add torsion to ghost ray biometric theory?
Yeah. Do you think it's possible? I mean, I think some people have done or not. I don't know. I'm not aware.
Yeah. Okay. So it could be possible. It would be possible. I cannot exclude it. The thing is, what they have done and still not completely understood is torsion gravity, which actually people refer to it as torsion by gravity because around Minkowski it propagates 7 degrees of freedom, the 2 of the graviton and the 5 of the, and that is just Einstein-Hilbert with a torsion. I mean, in the first order formulas with a torsion term. And in fact, at quadratic order, they have the exact same terms as as biometric theory people have. But there is also a term that couples, let me remember that, the massive spin-2 field to the background Ricci curvature, which Riemann tensor. So there is an extra term not predicted by Fitz-Pauli that appears there already at the quadratic level. And it's interesting because they propagate the same degrees of freedom around Minkowski, 2 + 5. And I think people are studying, as also we cite in our paper, they're studying now black hole solutions in that torsion by gravity theory, but it's actually very new. It's in the last 5 or so years that people started considering torsion by gravity.
Yeah. I'm asking also this because again, in condensed matter, torsion is also something important.
Okay.
And you know, again, I was just thinking a possible application outside the astrophysical, cosmological, field. Thank you.
Okay, no, thank you. That sounds very interesting, actually. But the condensed side, I don't know. That sounds. I mean, if one can connect, it would be amazing. If you get similar properties in both fields, that would be wonderful. Yeah.
Very good. Just one final comment. the two fields enter very symmetrically into your original action. Presumably, one of the motivations is that you want to explain why one of the masses would be, why one of the MF or MG would be larger, and that seems very natural in string context. You've got a massive, you only have a graviton, one graviton that's massless, and the other spin 2 has to be massive. So that looks like a very natural.
I see what you mean. That is a great point, actually. So in fact, let me say that this structure, with this structure and the properties of the elementary symmetric polynomials, one can show that it's very much symmetric under interchange of G and F.
Exactly, yeah.
Yeah. Now, as you very well point out, MG and MF cannot be equal. Otherwise, you don't get the correct phenomenology. But at the same time, considering limits where like the ratio is set to is approaching 0 or infinity, is also can also be problematic in the sense that you may run into strong coupling issues for one of the two metrics. So that's ambiguous. I wouldn't want to go into that. And also in our paper, we do not go into that, right? We do not, not even for alpha prime do we assume extreme values. We just consider a small alpha prime, but we do not strictly take the limit. So for all these kinds of parameters, one has to be very careful where they're in both the field and the string theory side, what their values are.
Yeah, and I'm wondering what the supersymmetric version of this would be.
Yeah.
Has somebody supersymmetrized it, gone to the analog of 11-dimensional supergravity for this?
But you see, when I came to Munich, actually in the proposal I had written that I would want to supersymmetrize this theory. Okay. And I tried several things. Also, I was working together with Agnes at the time when we were working together in this, and we couldn't find a way. So I tried first in the component notation. It didn't seem straightforward because G and F are not mass eigenstates. That's part of the problem, okay? And if you work in a mass eigenstate basis around Minkowski, okay, that's well known. There are many papers, I think Zinoviev wrote out the massive spin 2 Lagrangian. So independently, you can write, around Minkowski, you can write supersymmetric actions. The question is, can you do it fully non-linearly? And then I tried the, in the Wessenberger notation, so, excuse me?
Sorry, no, I mean, somehow I suspect you can't go to that high dimension. One should think a lot more along the lines of Werner's original argument for 11-dimensional supergravity.
You mean to not start with 4D, but go to 11D?
Well, no, I'm just saying the argument was what is allowed. How can I supersymmetrize this, and what dimensions are allowed for?
Okay, I don't have an argument against 4D. Maybe let me continue with what I was trying to see. Maybe this, no, please. No, maybe this will be more helpful. The thing is, we tried the superfield notation first, so after the component. So first the Wessenberger notation, using a curvature superfield, chiral curvature superfield in a field line chiral density. And again, there were issues there because that curvature superfield contains the Ricci scalar. And so if you try to write products like these kinds of products, but for superfields, then you don't get just this structure if you expand in component fields. You get also products of Ricci scalars. And this would excite the ghost because we know this is the unique ghost free action, okay? So again, I said, okay, the ER, the Wessenberger notation will not work. And then I discovered that there is this amazing formulation of formulation of supergravity from Ozhievetsky and Sokachev. Yes. Maybe you know the H mu, this axial gravitational superfield. And in fact, this contains the field bind as a component, not the metric, and not the Ricci scalar. And then I tried to consider products of two different such superfields, but again, it didn't work. Then there was an issue with preserving both one copy of supersymmetry and one copy of Livio invariance. So I have really worked a lot on this. I have not managed to do it. Maybe it's possible. I cannot exclude it. Yes. We certainly a very interesting question. Yes.
Yeah, that's Very interesting. Thank you for a stimulating talk. That was, I mean, are there other questions? If not, I will thank you. We tend to run on endlessly almost, but so I'm going to stop the recording. Thank you again.
Sure.
We can continue chatting.